Hello, welcome back. This is another Big Idea 4 example problem right here. And so what I have is a set of data, and I kind of want to show you some of the things that you can do with a set of data. Now, you've probably been seeing lots of data like this, but first of all, you want to look at the elements that you have. So you have 3 trials. Here's your overall reaction right here. This is your initial starting concentrations of your different reactants. And here's your initial rate of one of your products. And it's moles per minute. A lot of times you see moles per second. So keep that in mind if it's moles per minute, because you're going to need to keep that unit when you answer your question. All right, so let's take a look here. What are some things we can tell right off the bat? Well, one of the first things you always want to do with some of this data is you want to go ahead and try to figure out the rate law. Okay, so the rate law, rate, is going to equal the constant times the concentration of these two elements. So we have, the concentration of these two reactants, not elements. And what we want to do is we want to figure out these numbers right up here. We want to figure out the orders from our data. So let's take a look right here. So first of all, in our first reaction, we have 0.1 and 0.1, and our rate is 1.5 times 10 to the third. In the second trial, we double both of them. Now, when we double both of them, it only doubles the overall rate. So that means that one of these is doing something to the first order, and the other one isn't. So let's look at our third. And so when we look in our third, what we've done is we've doubled A, and we've left B alone. So from 2 to 3, we doubled B, and look at the rate did not change. So that tells you that A is not affecting the rate. So A up here, we can go ahead and write this. A is going to be 0 order, and B is going to be the first order. Now, if you ever have a 0 order reactant, you do not have to write it in the rate law. So the rate in this case is going to be K equals the concentration of B to the first order, because A doesn't affect it. So let's go ahead and analyze then. One of the things that they ask you to do sometimes is they ask you to look at mechanisms and say, which mechanism matches the data? So what you want to do with these mechanisms is essentially just add them like you're doing a addition problem, okay? So let me just do this real quick. So let's just say we have this mechanism. We're going to take this and we're going to add these all up. So first of all, let's add up all the reactants. So we have A's. So I have 2 A's plus a B plus 1 E for my reactants. And then now I'm going to add up all of my products over here. I have a C plus a D plus an E. Now what you want to do is you want to go ahead and eliminate any intermediates. So intermediates are anything that show up in the mechanisms, and these are the steps that it takes to do this overall reaction right here. So anything that shows up in these steps that is not in the overall reaction is what we call an intermediate. So you'll notice that E right here in both of these situations is something that's not in the overall reaction. So if we go down here and we cancel out these E's, we find that indeed it's 2A plus B goes to C plus D. So that's good. So yes, so far this matches up. But now there's one more thing. We determined that our rate law was our constant times the concentration of B to the first order. Now your slow step determines your rate law. And so you have to use this entire slow step for your rate law. If you look at this slow step, it's got this as the rate law. It's got essentially, if you look at this right here, we've got A plus B. So what that's saying is that's saying K times the concentration of A to the first order to the concentration of B to the first order. Has both of those in there. So because of that, that's a big fat no. All right, so this isn't going to work because we know that we only have B. So this first set we could cancel out because it does not match up to the rate law. So let's look at mechanism 2, and possibly both of these won't work. But let's go ahead and try this mechanism too. But we have been able to, from the data, eliminate this as a possible mechanism. So this mechanism here, we've got, let's go ahead and add these all up. So I've got a B plus, I've got two A's in here on my I'm just adding up all my reactants, plus an E, plus an F, and then that's going to go to the other side. So I've got a C, plus an E, plus an F, plus a D. All right, once again, I'm going to go ahead and get rid of all my intermediates. So I see two intermediates in here. I don't want this, I don't want that, I don't want that, and I don't want that. So that's going to eliminate that, 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 and that. And sure enough, here we are. We are at 2A plus B goes to C plus D. So this mechanism does add up to our overall reaction, right? So then the question is, does this step here, the slow step, because remember the slow step determines the overall rate. And look, in the slow step, we have just B turning into C and E. So the slow step here is saying that we have just B to the first order, because it's just one of them. So this one matches up to both the rate law and the overall reaction. So yes, indeedy, this is it. Woohoo! All right. There's a couple other things that we can do with this right here. Let's go ahead and get rid of some of that. There's a couple other things that we can do with this. For example, we could calculate the half-life. Let's just go ahead and calculate the half-life. So the half-life is going to be first order, because we just have the one we have the one reactant. So let's calculate the half-life of B. So reactant B. So B, the half-life is going to equal, let's see. So the half-life of B is going to equal, I don't need to draw that in brackets. I don't know what I'm doing there. Okay, so B, half-life. Okay. So that's going to equal, we know that a half-life for a first order is 0.693 divided by the rate constant. Now, we're going to have to solve for this rate constant real quick, which is pretty easy. Let's just take this first one right here. So we know that the rate is going to be 1.5 times 10 to the third is going to equal the rate constant times the B to the first order, and A is not included. So if we divide 1.5 times 0.1, we're going to get the K as 1.5 times 10 to the second, right? Now let's go ahead and, go ahead and write that a little bit neater, and not that it really matters. And so K equals that. So if I divide that by that, let's see, 0.693 divided by 1.5 times 10 to the second, or 150, 46. In this case, it's going to be minutes, because this is moles per minute. So something to keep in mind is this unit right here. When you're looking at the, you add in this molarity and the appearance of this, it's always going to have to match up to the units that's given right there. What's another thing we could do? Well, what if I was to ask you the total amount of D if experiment 1 was allowed to go to completion? So if I said I was going to let experiment 1 go all the way to completion, so what would that give me? Well, here's what you would do for that. You would look at the overall reaction, and you would say, all right, look, there's 2 A's to every 1 D that comes out. So if I put in 0.1 mole of A, right, when it comes out as it comes out a D on the other side, it's going to be exactly half of that. So it's 0.05 molar if it was allowed to go to completion. So anyway, so that I hope helps just kind of take some of this data and give you an idea of how to get lots of different information, solve lots of different problems they might ask you for from a set of data like that.